Hello geometry students, my name is Jami Emigh, and this video is our discussion on section 1.5, angles and their measure. We are getting into defined terms now, unlike the undefined terms we were talking about earlier. Our next defined term is an angle. It consists of two different rays with a common endpoint. You have a nice visual on an angle here. Point A, we call the vertex. That is that common endpoint of the two rays. It's called a vertex. The sides are the rays AC and AB for this particular angle. Notice when we name the rays, they both start at the letter A, and the arrow on the symbol above is over the C and the B, not over the A. You can name this particular angle in 4 different ways. You can call it angle A, like you see there, capital A, using the vertex. You can name it angle 1. That is because this 1 right here is just like a label. Has nothing to do with measure or a point on the angle. It's just a label, like a label on your shirt. This is number 1. You can name the angle using 3 letters. 1 letter on one of the rays, followed by the vertex, followed by a letter on one of the other rays. And this 4th way is in the same fashion, just goes in the other order. Goes from a letter on one of the rays, followed by the vertex, followed by a letter on the other ray. So we have enough information, enough labels on this particular figure to name this angle in 4 different ways. You don't always have enough labels or information to name an angle in 4 ways, but if you do have enough, then there is a maximum of 4 different ways. Well, not max. I shouldn't say max, because if we knew another dot right here, let's say that point was D, then you could name that angle DAB. One more thing I want to point out, in some text, you'll see the angle symbol have a arch through it like that. And same thing, just a different type of notation. The interior of the angle, it's part of a plane. It contains all of the points between the 2 sides of the angle. You can see this shaded here. And the exterior of an angle contains all the points that are not in the interior of the angle and are not on the angle. So not on the angle either. So it would be this shaded region here. All right, let's try an example about identifying and naming angles. Part A, how many different angles are in this diagram? What do you think? How many angles do you see? If you said 3, you got it correct. Nice job. The 3 angles are angle 1, so this one here, angle 2, so this one here, and then also this one you may have missed, angle MPQ, so that's the large one there. Okay, part B, write 2 other ways to name angle 1. So focus on this angle right here and write that in 2 other ways, please. If you came up with angle MPN or angle NPM, you got it right. Good job. So M is on one ray, P is the vertex, followed by N. And then the other direction, N is on one ray, P is the vertex, and M is on the other ray. Classifying angles. So classifying means group them, and each group has a name. So acute angles, that's a group. And the name of that group is acute angles. The angles that make it into that group or qualify as acute angles are angles that have measures between 0 and 90. Notice that it's strictly between 0 and 90. It's not including 0 and 90. And the way you notice that is that inequality right there is just strictly less than, strictly less than. Okay, Here's a visual on an acute angle. If I had to guess, maybe this is like a 70-degree angle. That would qualify as acute because it's between 0 and 90. Our next group of angles has the title right angles. And for an angle to qualify into this group, its measure has to be exactly 90 degrees. I'd like to just picture the corner of the desk you're sitting at, or the corner of really anything. Just think of a sharp corner when you driving your car, if you turn the corner there, or if you look at the edge of your window or your door and you see a corner, it's typically a 90-degree angle. They should be nice and easy to spot. Geometric code, though, needed would be that code right there, or you could just have it say 90 degrees. And you can see there, mine doesn't look like 90 degrees. It actually looks smaller than 90, but by writing that 90 there, that's more powerful than my lack of perfection on my sketch. The next group of angles has the title obtuse angles, and the angles that make it into this group are angles between the measures of 90 and 180. Okay, so it's got to be greater than 90, but less than 180. So you can see how this opens up a bit further than a right angle. If I had to guess, maybe that's like 105 degrees. Okay. And the last group of angles classified based on their degree measure, I want to point that out real quick. All of these are based on classified angles based on degree measurements. Degree measures. All right, last one is the group of straight angles, and the angles that qualify as into this group are angles with exactly 180 degrees, and that makes a straight line there. D is the vertex, and you'll often see an arch over that, just so to clarify that you're talking about angle D versus just a point on that line. All right, so last thing I want to point out on this slide before I move on is the lowercase m in front of each of these angle measures. If you see that lowercase m, then they are addressing the number of degrees that the angle measures. Other common unit would be radians, but we're starting with degrees. We'll talk about radians in the near future. Two angles that have the same measure are called congruent angles. This is very similar to two segments that have the same measure. Those are called congruent segments. So recall from the congruent segments definition, this symbol right here is what we use for congruent. I like to think of it as an equal sign, so equal measure, but it has this additional part right here, right there above, denoting congruency. We mark the congruent angles with exactly the same number of arcs. So in this scenario here, we have these two angles, C and D, and so we use one arc. In this scenario here, you can maybe mark off these ones with a single arc, but if the single arc is already used up, then you can step it up to two arcs. And if you're in the same scenario and you need to mark off more congruent angles, you can use 3 arcs or 4, okay? But any angle with exactly the same number of arcs is a geometric code for congruent angles, which means that they have equal measure. All right, so let's try a scenario here. If the measure of angle C equals 45 degrees, and I always write it on the figure if it's reasonable to do so, then the measure of angle D equals how many degrees? What do you think? If you said 45 degrees, you got it right. Nice job. If the measure of angle 3 equals 113 degrees, what do you think the measure of angle 4 is? If you said 113 degrees, you got it right. Nice job. Congruent angles versus equal angle measures. You guys saw this almost identical with segment lengths. So if angle A is congruent to angle B, then the measure of angle A is equal to the measure of angle B. You have to notice the difference in that notation. It's subtle, but it's important. We use the congruent symbol when we're talking about the actual shapes. We use the equal sign when we're talking about the measure. And the converse of that statement is true. If the measures are equal, then the angles are congruent. So over here, we would be able to say that angle A is congruent to angle B, but that angle, the measure of angle A, is equal to the measure of angle B. So the point of this here is really emphasizing when you can use the congruent symbol and when you're supposed to use the equal symbol. Angle addition postulate. Just like the segment addition postulate, you're allowed to add angle measures. And that's because the unit of degrees or radians, they follow the rules of addition. So we're allowed to add angle measures together. And if you're ever justifying why you're able to add angle measures together in a proof, you would say due to the angle addition postulate. All right, so the postulate says if P is in the interior of angle ABC, then the measure of angle ABP plus the measure of angle PBC equals the measure of angle ABC. Let's get a visual on that. Oh, they didn't draw one for us. Let's draw it ourselves then. All right, so let's say we have this angle ABC. A would be on one ray, B would be your vertex, it has to be because it's in the middle, okay? C. So here's our angle, and it says that if P is in the interior, so I can put P anywhere inside of here. So maybe here, I'll put P right there. Okay, it says that then the measure of angle ABP. So ABP, let me change colors to highlight it for you, would be like this. A to B passing through P. Okay, plus, let me change colors again to highlight, the measure of PBC. So that would be from here to B passing through C. Well, those colors are kind of similar, sorry, the light blue and the light purple. Then that would equal the whole measure A to B to C. Let me try to put some numbers that might help us. All right, let's say that ABP is a 20-degree angle. And let's say that PBC, it looks a little smaller just based on the way I drew it. So let's go with a 15-degree angle. So the postulate says that the 20 degrees plus the 15 degrees, you're allowed to add them to get the measure of angle ABC, which would then be 35 degrees. At this point, it'd be a little hard to label that. So one way to do so would be to draw an arch like that and then write the 35 degrees. That's a way to represent this entire angle. The large one measures 35 degrees. All right, I hope that helps. This example will also help. If DEG is a right angle, okay, I always like to trace it with my finger on the figure just to make sure I'm seeing it and touching it and committing it to my memory or really thinking about it. Then we are asked to find the measure of angle DEF. So we're asked to find DEF, which is represented by this expression here. And we're asked to find the measure of FEG, which is represented by this expression here. All right, so we need to find those two angle measures. Notice that each algebraic expression has the letter x in them. So we are tasked with writing an equation, an algebraic equation. We want it to have an equal sign because that's what makes it an equation, and we want it to have the letter x in it. So looking at your figure, we have to translate. We have to be bilingual in this class. A lot of translating from geometric figures to algebraic equations, just like translating from English to Spanish. All right, so we need to translate from this figure to an algebraic equation. And the angle addition postulate is what is going to allow us to make that translation. So I'm going to write here that the measure of angle DEF plus the measure of angle FEG is equal to the measure of, and now I'm going to write the large one, DEG. That right there is the angle addition postulate. Now we're going to take it from these letters into the algebraic expressions. DEF is this one here, 3x plus 5, plus sign. FEG is this one right here, 10x minus 6, equal sign. And then DEG is the large one. What are we going to write for the large one? Well, we know its exact measure. It's 90 degrees. We were told that right at the beginning, and it has that code. So we set that equal to 90 degrees. Okay? I said it before, you guys, this is going to be a very necessary skill for us to to succeed in learning about geometry, translating from a geometric figure to an algebraic equation like that. At that point, you can say to yourself, okay, just pretend I'm back in algebra class and do my manipulating of equations here. First thing I did was combine like terms, and then I'll use the addition postulate of equality, adding 1 to both sides, and then I'll use the division. Did I say postulate? Gosh, I'm drawing a blank here. Division, postulate of equality. Is it a postulate? Oh, I'll get back to you on that. But divide both sides by 13. Oh, and I wrote something wrong because I got distracted on what that is called. Dividing both sides of the equation by 13. And 91 divided by 13. I'm going to have to pull my calculator out for that one real quick. 91 divided by 13 is 7. So we found our x equals 7. We'll then plug that back in. Now this just looks like a humongous mess, so let me erase all my scratch work and I will show it to you written up a bit nicer. Okay, there is our translation into our algebraic equation. And there's the work. Much nicer and easier to see than what I wrote with my finger. Now taking that 7, plug it back in right there. Tells us that the measure of DEF is 26 degrees. Plugging that 7 in right here tells us the measure of FEG is 64 degrees. And I believe that's all we were asked to do. One quick way to check my work, it only takes a second and it's worth it to make sure I didn't make a mistake. These should add up to 90, which they do. Okay. Angle addition postulate. All right, so the other common unit for measuring angles is radians. So degrees and radians, those are the two most common. A measure of an angle in radians is the length of the arc of a circle intercepted by the angle. Let me try to explain. When you're measuring in degrees, it's this amount that the angle opens up. And when you're measuring in radians, it's the same angle. It's just the length of this arc right there. So the length of the arc of the circle intercepted. And here's what I mean by intercepted. I'm talking about this 45-degree angle, by the way. Intercepted. So let's say you're, I don't know if you play baseball or anything, but if you throw the ball or if you run and you run to there, and then the other situation you throw or run to here, you have intercepted the circle here and here. So this is the arc that you have intercepted. So however long that arc is, that is the radian measure of the angle. If you go all the way around the circle, that's the whole circumference of the circle. And circumference of the circle is 2 pi. So you already knew one radian measure. You guys calculate that quite frequently. Let's erase my work there and show this. All right, the first figure is the unit circle measure in degrees. The second figure is the unit measure in radians. So I want to point out a couple equivalencies. 45-degree angles have a measure of pi over 4 radians. A 90-degree angle has a measure of pi over 2 radians. Now, this angle is obtuse. This 135-degree angle, it has a measure of 3 pi over 4 radians. That would be this angle here. And so that means that this arc is 3 pi over 4. That's the measure of its length. All right, this one you guys should be able to see nicely. The straight angle, 180 degrees, so that's this angle here. That is the measure of pi radians. I'm going to erase the other work and elaborate on this one. So this angle right here is 180 degrees, and this arc right here is pi radians. 360 degrees is if you go all the way around the circle, and 2 pi radians is if you go all the way around the circle. So let's say we only went halfway around the circle. So we divide that by 2. So we're talking 180 degrees. And if we, instead of going all the way around the circle here, we only went halfway. So divide that by 2, and that's where the pi radians comes in. So 180 degrees is pi radians, equivalent to pi radians. All right, 225-degree angle. So that's an angle that starts here and opens all the way up past 180 degrees. That would be equivalent to 5 pi over 4 radians. If you go 3/4 of the way, 270 degrees, then you are at 3 pi over 2 radians. Almost all the way around the circle, so now we're at 315 degrees. Excuse me. All right, almost all the way around the circle to 350 degrees. 15 degrees is an arc length of 7 pi over 4 radians. And the last one, I'm going to erase everything else. The last one, if your angle starts right here and opens up and goes all the way around the circle, that is a measure of 360 degrees. And in radians, if the arc is intercepted here and goes all the way around and is intercepted there again, that is 2 pi. Okay. The 2 pi comes from circumference of a circle equals 2 pi r. But r in this unit circle, I didn't really emphasize it yet, sorry. The r in a unit circle, the radius is 1. So this circle that I've been addressing has a radius of 1. It's written right here, but I didn't really highlight it too much. So radius of 1, 1. Here we're at -1, here we're at -1, and that's because this radius it's still +1 because the length has to be positive. So these unit circles have a radius of 1, so that would make it 2 pi times 1, which is where we get the 2 pi from, okay? The unit circle, radius of 1. All right, here's our unit circle again, a radius of 1, but this time this figure has the degrees and the radians labeled on the same figure, so you can see them in the same place. So 360 degrees equals 2 pi, 30 degrees equals pi over 6, and here's the table for you as well. 360 degrees equals 2 pi, 30 degrees equals pi over 6, and they're the main ones are listed here, the most frequently used ones. 45 degrees is the same as pi over 4, also listed here in the table. 60 degrees is pi over 3, also listed here in the table, and so on. So you might want to print this. It'll be useful throughout this class and throughout trigonometry if you decide to go that route, or Math 28 for education. Really just useful for any learning experience in mathematics. Okay, so let's talk about if you don't have the figure and you don't have the table, can you do the conversion on your own? And the formula to convert between degrees and radians is pretty simple. So to take 45 degrees and change that to radians, you take your 45 degrees and you multiply it by pi over 180. Okay, pi is the radians measure, 180 is the degrees measure. So what's going to happen, the degree units, they're going to cancel out because one is on the top as a numerator and one is on the bottom as a denominator. Let me erase my work and show that again. The degree units are going to cancel out because one's on the numerator and one's a denominator. And what you're left with is the unit of radians. So that's how we convert from degrees to radians. 45 divided by 180 is 1/4, and then pi remains on the top. So 45 degrees in radians is pi over 4 radians. All right, let's try the opposite route. We're given pi over 2 radians, and this time we want to know what that is in degrees. Now, if you don't have the figure and you don't have the table, what you do is take your pi over 2 radians, and this time you multiply it by the inverse. Okay, you flip these two. 180 degrees is on the top, and pi radians is on the bottom this time. The reason why you want to flip them, well, one way to help you remember to flip them, I should say, is this radians is a numerator here, and it's a denominator here, which means they'll cancel out, leaving us with the unit that we want, degrees. So always set this up so that your current unit cancels out and you're left with the unit that you want. So for this one here, pi would also cancel out. And then we have 180 divided by 2, which is how we get the 90 degrees. I want to write this a little simpler. If you're trying to get from degrees to radians, I wonder if I already put it. No, I didn't. I want to write this a little simpler. If you're trying to get from degrees to radians, multiply by pi over 180. And if you're trying to get from radians to degrees, you'll multiply by the inverse, which is 180 over pi. The reason that is written out simpler is I just didn't write the units. So here's the pi over 180 that I was talking about. I just left off the units of radians and degrees. And here's the 180 over pi that I wrote here. I just left off the degrees and the radians, which is simpler, yes, but it can also be risky writing stuff without the units, because the units are really what help us see the cancellation of degrees and being left behind with radians, or the cancellation of pi radians and being left behind with degrees. So either way, do which way you feel most comfortable with. They're the same thing. It's just this one wrote the units and this one does not. Wanted to give you a visual on a protractor here. 0 degrees. If you're ever asked to measure an angle using this tool, you put the vertex of the angle right here at Q, okay? Vertex of the angle always goes there. And then you line up one of the rays with this one here. Even if you have to twist your paper or twist your angle or twist the protractor, you've got to get the vertex set up there and one ray set up there. That's the setup. After that, you'll measure where the other angle, the other ray lands. So if the other ray lands right here, that would make it a 130-degree angle. If the other ray lands here, 45 degrees. If the other ray lands here, 165 degrees. And I'm using, because I lined mine up here and I'm opening my angles up this direction, I'm using the numbers on the bottom row, if you will. These ones here, 10 degrees, 20 degrees, 30 degrees, 40 degrees, which makes sense because then we get to 90 degrees. That would be our right angle. And then we go into obtuse measurements. And then we land at our straight angle measurement, 180 degrees. All right, that will conclude our discussion on section 1.5. My name is Jamie Emigh. Thank you for joining me, and I'll see you next time for our discussion on section 1.6.